So hello everyone. Now this is topic 9, which has to do with process flow measures. And now what's very important in the topic is to understand the three very important measurement that we will take. The first one is the flow time. So the flow time right here. The second one is the flow rate, which is R, and inventory is I. So let's look at the check-in process at an airport. So when you go to check-in, there's customers walking in, check-in process, and after they do the check-in, there's customers leaving. And in the middle of the process, there are customers stuck in the process or being served or waiting. We call that inventory I. The rate at which customers come in and leave, we call that R. And then the time it takes for so a time and an average customer spends in the system from the beginning walking in to walking out is T. So that's flow time T. While R is the flow rate and inventory is I. And all these numbers are average numbers. This is very important to remember that these are all average numbers. So a process, we have inflow in a process and outflow in a process, and in the process we have, it could be, as we said, it could be product, it could be customers are stuck in a process in terms of inventory. Now when the inflow exceeds outflow, so the inflow is much greater than the outflow, and you see this in places in the early morning where you have more customers coming in than leaving. In that case, inventory will increase. So I will increase in that case. So in the first case, I will increase. Now, when the outflow rate is higher than the inflow rate, so more people leaving the process than entering the process, then inventory is gonna go down. Now, what we just mentioned is all in the short term. In a long term, we get more of a stable process where the inflow rate, so in a process, the inflow is going to be equal to outflow. So R is going to be the same whether you measure it at the inflow or you measure it at the outflow. And we call that throughput. So that's a new terminology, we call that throughput. So again, we call R, it is the average inflow rate, the average outflow rate, and it's also the throughput of the system, of the process. And now we get the same definition in terms of T and I. But what's very important about a stable process is that we get to use Little's law. Little's law is basically this very important relationship that is going to relate R, T, and I. So whenever you have one of these three variables not known, you could actually calculate it using this equation. So let's see an example on Little's law. Now, this is the time when you should pause the video and read the example and try to do it on your own before you could play the video again. Now, we have a toy manufacturer. That toy manufacturer had a throughput rate of 30. So this 30 is basically R. And it takes 0.5 hours for a toy to go through the process. So we have 0.4 hours, it takes time, and we know that this is T, this is the time it takes for the flow unit to go from the beginning of the process to the end of the process. So that's T right here. How many toys on average how many toys are on average in the process. Now they're asking us for I. What's stuck in the process on average is basically I. So this is the throughput. This is the flow time. We don't know inventory, so inventory is our unknown. So we just use our equation, I equals to R times T, and we get 15 toys. So let's see another example. Now with this example, again, pause the video, read the example, try to do it on your own, and then play the video again. So we're looking at a local deli where people arrive at a rate of 30 per hour. So that's basically your R. Remember, arrival rate and output rate has to do with R. On average, there are 8 people waiting in the line to be served. So this is people inside the process. So we're looking at I. Once a person gets to the counter, it takes average 5 minutes to be served. What is the flow unit? So the first question is, what is the flow unit? And in this case, the flow unit are basically people. The flow units are people because people are coming into the deli. Now let's draw the process. Now the process here is a little bit more complicated. We have two different things, two different processes. We have the waiting. So when you walk into the deli, there is waiting, and then there is the actual service. Now with the check-in process, when we talked about the check-in process, we didn't go into detail. We just said the whole check-in is a process. For this, we have two different numbers, one for waiting, one for service. So we have two different processes, and there's people coming in, waiting, and once the waiting is done, they get serviced. The service takes 5 minutes, and then they're out. So now the question asks, how long does a person wait in line? How many people are being served on average? How many people are in the deli on average? How long does it take a person to go through the process? The challenge in this problem, is that we have a process broken down to two processes, and we're going to see a lot of example like this. We're going to see later on the hospital example where we have maybe 6, 7 different processes. And so it's very important to us to understand that there's two different elements or different processes, which are the waiting in line and the actual service. So we've shown that in the diagram where you have this is waiting, this is service, and then you're out. You see a lot of our examples, we use triangle to basically represent a waiting process, and square for a normal process. So in the deli, we have this situation here, and they're giving us numbers. So for example, there's 8 people waiting in line. So we know I for the triangle, the waiting is equal to 8. And we know that the service takes 5 minutes. So we know I for the first process, and we know T for the second process. And very important, R is going to remain the same, because with laws, Little's law, we know that in a long run, in a stable process, the inflow is equal to the outflow. So R is going to be the same everywhere. So the rate of customers walking in and moving through the process is going to be the same. Now, very important, this might change when the flow unit change, and we will see that in later examples. So now we go on. So we'll calculate R in terms of minute, because all our other numbers are in minutes. So if we have 30 per hour, we get 0.5 per minute. We just divide by 60. Flow time is 5 minutes. We've already mentioned this. and the people inventory in the waiting line is 8. So if we draw a table, then if we look at the different parts of the process, we have the waiting line, which is 1, and then being serviced is 2 in terms of the process. We know the inventory waiting line, we know the throughput, then we could right away calculate the T using the equation. So the equation T basically is equal to I over I over R, and this is just rearranging the equation. And by calculating, so when you go 8 divided by 0.5, it's going to give us 16. Now, the problem becomes really simple when we organize ourselves and we think of the process in terms of 2 parts, waiting line being served. That's going to help us in answering the question. Now, being served, we know that the R is still the same, 0.5, and we have the time. Now what we need to do is calculate the inventory, and that's what the question is asking, how many people are being served. So R times T, which is 0.5 times 5, is going to give us 2.5. Okay. Now, if we want to know the total number of people in the deli, which basically means waiting line plus being serviced, then we have to sum these two numbers. The throughput, we don't sum the throughput. This is very important. This is a common error students make. You don't sum throughput. You only sum inventory and you sum the times too. So if we want to know how long the whole process took, is again, we have to sum 16 plus 5, 21. Now, again, here we have a process. We divided it into 2 parts. You could think of it as 2 processes. But we're looking at it here in terms of parts, so 2 parts. Throughput, we don't add throughput. This is very important. Throughput is a rate. You don't add rates. We add the inventory and the flow time for the overall process. Now, when the flow unit changes, and we're going to see that later in other questions, that's going to create a lot of problems for us, and once we get to this question, we'll show you how to deal with that. Now let's see question number, this example, an insurance company. This is a straightforward example. So the flow rate of, basically here, the flow rate is money, claims. So you have 10,000 per year, and the average processing time is 3 weeks, and this is T. So how many claims are being processed at any given time. So how many claims are in the process? So if we think of this, so this is an insurance company that's processing claims. So their output and input is basically how many claims they're getting is R. And that's what we said. So 10,000 per year. And the average processing time is 3 weeks. So this T is equal to 3. But what we don't know is inventory. How many claims are being processed at any given point in the process? And to do this, we just use the equation. Since we have R and T, all we have to do is convert T to years, because we have it in terms of weeks, and R is in terms of years. Again, it's very important to make your units match. So if one of your units is in hours, the other there. So if here in this case our R is in terms of years, so we have to have our flow time in terms of years. So again, this is another question. Again, pause the video so you could read the question and try to absorb it and try to do it on your own. So let's get to it. So we have a manufacturer that builds about $300 million worth of cellular equipment per year. So this is our R. So R, a lot of times R is going to feel like the annual demand, so remember when in your COM 225, when we had the annual demand for something in these inventory problems, that annual demand is really R. And in this case, R is here. The average amounts in accounts receivable, and this is going to be I, inventory. How much time elapses from the time customers billed? So they're looking for T. This is what they're looking for, this question. So we know what R is, we know what I is, and then we just calculate T using, again, Little Law equation. So Little Law equation is going to allow us to do so many different problems. So far we've learned the throughput, which is R, flow time, which is T, and inventory, which is I. But there are other interesting things that we have to learn in operations. We have the takt time and inventory turnover. And basically, takt time is really the time between one unit till next unit in production. So basically, think of it, if you're standing outside of a production line and you're timing the time between one product and the consecutive, this next product, that time is really takt time. And that takt time works out to be 1 over R. So it's the reciprocal of R. So whatever R is, if you take the inverse of it, you're going to get takt time. And if you're doing this, and if you substitute this into the Little's law equation, then we're going to get takt time equal to T over I. Inventory turnover is basically very important, is how many times the inventory is sold and replaced. So how many times are you selling and replacing that inventory during a time period? So if you have a turnover of 3 in 1 year, it means that you sold your inventory 3 times and you replenish your inventory 3 times. And that's basically the reciprocal of T. So takt time is the reciprocal of R. Inventory turnover is the reciprocal of T. And when you take into account Little's law equation, then it's basically R over I, just substituting the 1 over T into that equation. And so now let's take an example on takt time. So we have a medium car manufacturer which has an inventory. So this is our I. First of all, the takt time equation is T over I. And all these equations, remember, all these equations are going to be with you. Most probably you will write an online exam, final examination, which means you could write down all these equations, prepare them when you're doing the examination. So we have an inventory of 150,000 cars. That's how much they told us the inventory is. And the time is, they're telling us the duration is 2 years. So we know that there's 8 hours per day, and we know there's 250 operational days per year. So we could get the T, the overall T, which is 4,000. And then takt time would be T over I, and it's going to be 4,000 over 150,000, which is 0.026 hours per car or 96 seconds per car. Now, don't mistake this number. Don't think that it means that it takes 90 seconds to produce a car. That's not correct. What that means is that when you're producing these cars, if you're standing outside of the production line, every 90 seconds, the production line is going to spit out a car. That's basically what it means.